Hello friends! Disclaimer. As an Amazon associate, I earn from qualifying purchases at no additional cost to you. Please don't forget to check out product links for stargazing in the description of the video. A quasar is an extremely luminous and distant active galactic nucleus, AGN, powered by a supermassive black hole. It's essentially a cosmic powerhouse, emitting tremendous amounts of energy as matter swirls around and falls into the black hole. Quasars, short for quasi-stellar objects, are among the most powerful and enigmatic phenomena in the universe. They shine with an intensity that outshines entire galaxies, even though they are incredibly compact in size. But what makes quasars truly mind-bending is not just their brightness. It's the incredible forces at work within them, the distant past they reveal, and the complex interactions they have with their surroundings. In this video, we'll dive deep into the science of quasars, exploring everything from their basic characteristics to the advanced theories that try to explain their behavior. Quasars are a type of active galactic nucleus, or AGN, which refers to the extremely bright central regions of certain galaxies. These regions are powered by supermassive black holes that are actively pulling in and consuming surrounding material, such as gas and dust. The process of accretion generates tremendous amounts of energy, making AGNs some of the brightest objects in the universe. However, not all AGNs are the same, and quasars are just one type within this broader category. To understand what makes quasars unique, it's helpful to compare them with other types of AGNs, such as blazars and Seyfert galaxies. Quasars are the most luminous type of AGN. They are powered by supermassive black holes that are actively accreting large amounts of material, which heats up and emits incredible amounts of energy. Quasars can outshine entire galaxies, and because they are often found at great distances from Earth, observing them allows astronomers to look back in time to the early universe. Quasars are characterized by their immense brightness and the fact that they emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays. The powerful radiation from a quasar can affect its entire host galaxy, influencing star formation and even pushing gas out of the galaxy. Blazars are another type of AGN, but they are different from quasars in a key way. While both quasars and blazars are powered by supermassive black holes, blazars are unique because of the orientation of their jets. In a blazar, one of the jets of high-energy particles produced by the black hole is pointed almost directly toward Earth. This alignment causes the light and radiation from the jet to be highly beamed, making the blazar appear extremely bright and variable when observed from Earth. This beaming effect also makes blazars some of the most variable and dynamic objects in the universe. Unlike quasars, where the accretion disk dominates the brightness, blazars' brightness is mainly due to the jet of particles pointed at us. Seyfert galaxies are another class of AGN, but they are generally less luminous than quasars. They are named after the American astronomer Carl Seyfert, who first identified them. Seyfert galaxies have bright, compact centers like quasars, but their host galaxies are more easily visible because the central AGN is not as overwhelmingly bright. Seyfert galaxies are often spiral galaxies like the Milky Way, and they are typically closer to Earth than quasars. Seyfert galaxies emit radiation primarily in the visible and ultraviolet ranges, and they are often characterized by strong emission lines in their spectra. While they are still very energetic, the black holes in Seyfert galaxies are not accreting material as rapidly as those in quasars, which is why they are not as luminous. Quasars are unique among AGNs for several reasons. First, their extreme luminosity sets them apart, making them some of the brightest objects in the universe. This brightness is due to the enormous amount of material being accreted by the supermassive black hole at their centers, which generates vast amounts of energy. Second, quasars are often found at great distances, meaning they represent an earlier stage in the universe's history. Observing quasars allows astronomers to study the conditions of the early universe and the formation of galaxies and supermassive black holes. Another unique aspect of quasars is their ability to influence their host galaxies on a large scale. The energy output from a quasar can drive powerful winds and jets that can push gas out of the galaxy, affecting star formation and even the overall evolution of the galaxy. This feedback mechanism is thought to play a critical role in the development of massive galaxies. Accretion disks are fascinating structures that form around supermassive black holes at the centers of galaxies, and they play a crucial role in the formation and activity of quasars. When gas, dust, and other material get close to a black hole, they don't fall directly into it. Instead, these materials start to spiral around the black hole, forming a flat disk-like structure known as an accretion disk. The reason this happens is due to the conservation of angular momentum. As the material gets closer to the black hole, it speeds up, much like a figure skater pulling their arms in to spin faster. The faster the material moves, the more it flattens out into a disk. As the material in the accretion disk orbits closer to the black hole, it experiences intense gravitational forces. These forces cause the material to collide and rub against itself, creating friction. This friction heats the material to extremely high temperatures, often reaching millions of degrees. The inner regions of the accretion disk, which are closest to the black hole, become the hottest and glow the brightest. The outer regions are cooler and emit less light. This process of heating through friction is what causes the accretion disk to shine so brightly across various wavelengths of light, from visible light to X-rays. The incredible energy output of accretion disks is one of the reasons why quasars are so powerful and bright. As the material in the accretion disk heats up due to friction, it begins to emit radiation. The hotter the material, the more energy it radiates. In the case of a quasar, the supermassive black hole at the center is so massive and the accretion disk so dense that the energy output can be staggering. In fact, the energy released by the accretion disk of a quasar can outshine an entire galaxy of stars. This energy is released in the form of electromagnetic radiation, which includes visible light, ultraviolet light, X-rays, and even gamma rays. The intense radiation pressure can push material away from the disk, creating powerful outflows or winds that can affect the surrounding galaxy. The energy output is so significant that it can influence the growth and evolution of the host galaxy, affecting star formation and the distribution of gas and dust. One of the key factors in determining the energy output of an accretion disk is the efficiency of the energy conversion process. The closer the material gets to the black hole, the more efficiently it can convert gravitational energy into radiation. In a quasar, this process is extremely efficient, which is why quasars are some of the most luminous objects in the universe. The brightness of a quasar is directly linked to the activity in its accretion disk. Because the accretion disk is so hot and radiates so much energy, it becomes the primary source of a quasar's luminosity. The light we see from a quasar is mostly the light emitted by the accretion disk, which can be so intense that it can outshine the entire galaxy in which the quasar resides. The more material that falls into the accretion disk, the more energy is released, and the brighter the quasar becomes. In addition to the light emitted by the accretion disk, quasars often produce powerful jets of particles that are launched from the regions near the black hole at nearly the speed of light. These jets can also contribute to the overall brightness of the quasar, especially when they are pointed in our direction. However, The majority of a quasar's brightness comes from the energy generated in the accretion disk. The brightness of a quasar can vary over time, depending on the amount of material being funneled into the accretion disk. When a lot of material is present, the quasar can become incredibly bright. When the supply of material decreases, the quasar's brightness may dim. This variability is one of the many intriguing aspects of quasars, making them a dynamic and ever-changing phenomenon in the universe. The formation of supermassive black holes, which are the engines that power quasars, is one of the most intriguing questions in modern astrophysics. These black holes, with masses millions to billions of times that of the Sun, are found at the centers of most large galaxies, including our own Milky Way. Understanding how these colossal objects formed is crucial to explaining how quasars work. Several theoretical models have been proposed to explain their formation, each offering different insights into how these massive black holes came to be. One of the leading models suggests that supermassive black holes formed from the direct collapse of massive gas clouds in the early universe. In this scenario, during the first few 100 million years after the Big Bang, large clouds of gas, mostly hydrogen and helium, began to collapse under their own gravity. If these clouds were massive enough, they could collapse directly into a black hole without first forming a star. These direct collapse black holes would start off with masses around 100,000 to 1 million times that of the Sun, providing a seed for the supermassive black holes we observe today. This model explains how black holes could grow so large in such a relatively short period of cosmic time. Another model proposes that supermassive black holes grew from smaller seed black holes, which formed from the deaths of the first stars, known as population 3 stars. These stars were much more massive than most stars we see today and lived short, violent lives, ending in supernova explosions that left behind black holes with masses around 100 to 1,000 times that of the Sun. Over time, these seed black holes could have grown by accreting gas and merging with other black holes to reach supermassive sizes. This hierarchical growth model is supported by observations of smaller black holes merging in the present-day universe, as seen through gravitational wave detections. A third model involves the rapid growth of black holes in dense star clusters. In this scenario, dense clusters of stars in the centers of galaxies could lead to repeated collisions and mergers of stars, forming a very massive star that eventually collapses into a black hole. This black hole would then continue to grow by accreting gas and by pulling in other stars, eventually becoming supermassive. This model explains how black holes in the centers of galaxies could have grown quickly, even in the early universe. Recent developments in computer simulations have also provided insights into the formation of supermassive black holes. These simulations suggest that the environment around these early black holes was crucial to their growth. For example, regions of space with high densities of gas and dark matter could have funneled material into the growing black holes, allowing them to accumulate mass rapidly. Additionally, feedback from the growing black holes, such as powerful winds and radiation, could regulate the amount of material falling into the black hole, influencing its growth. Once a supermassive black hole has formed, it can power a quasar by accreting or pulling in material from its surroundings. This process of accretion is the key to a quasar's incredible energy output. The material around the black hole, such as gas and dust, forms an accretion disk as it spirals inward. As this material gets closer to the black hole, it speeds up and heats up due to friction and other forces, reaching temperatures of millions of degrees. The intense heat causes the material to emit radiation across the electromagnetic spectrum, from radio waves to X-rays, making the quasar shine brilliantly. The energy released by the accretion process is what makes quasars so luminous. In fact, quasars can emit more energy in a single second than our entire sun will emit in its lifetime. The efficiency of this energy conversion process is remarkable. As material falls into the black hole, only a small fraction of its mass is actually swallowed by the black hole. The rest is converted into energy and radiated away. This efficiency is why quasars are among the brightest objects in the universe. Another important aspect of how supermassive black holes power quasars is the formation of jets. In many quasars, powerful jets of high-energy particles are launched from the regions near the black hole's poles. These jets are thought to be driven by the intense magnetic fields generated by the accretion disk. The particles in these jets are accelerated to nearly the speed of light and can extend for thousands of light years, interacting with the surrounding galaxy and beyond. These jets contribute to the quasar's overall brightness and can have a significant impact on the quasar's host galaxy. The exact mechanisms that govern the formation and behavior of these jets are still an active area of research. Scientists are using advanced simulations and observations to better understand how these jets are launched and how they interact with the environment around the quasar. What is clear, however, is that the combination of the accretion disk and the jets makes quasars incredibly powerful and dynamic objects. The formation of supermassive black holes and the process of accretion are central to understanding how quasars work. The latest theoretical models, including direct collapse, seed black hole growth, and star cluster dynamics, offer different pathways for the formation of these massive objects. Once formed, these black holes can power quasars through the process of accretion, releasing vast amounts of energy and driving powerful jets. These processes make quasars not only bright, but also fascinating objects that continue to challenge our understanding of the universe. One of the most remarkable discoveries in recent years is a quasar that is 500 trillion times brighter than the Sun. This quasar, named SDSS J0100 plus 2802, is located about 12.8 billion light-years away from Earth. What makes this quasar so extraordinary is not just its brightness, but also the fact that it existed when the universe was only about 900 million years old, which is relatively soon after the Big Bang. This discovery has provided valuable insights into the early universe and the formation of supermassive black holes. SDSS J0100 plus 2802 is powered by a supermassive black hole with a mass of about 12 billion times that of the Sun. The size and mass of this black hole are astonishing, especially given its age. The fact that such a massive black hole could exist so early in the universe's history challenges existing theories about black hole formation and growth. To reach this size in such a short period, the black hole must have grown extremely rapidly, either by accreting large amounts of material or through the merging of smaller black holes. The brightness of SDSS J0100 plus 2802 is another key feature that makes it significant. Because it is so bright, it can be observed at a great distance, allowing astronomers to study the conditions of the early universe. The light from this quasar has taken almost 13 billion years to reach us, meaning we are seeing it as it was when the universe was still in its infancy. This provides a unique opportunity to study the early stages of galaxy formation, the growth of supermassive black holes, and the reionization of the universe, a period when the first stars and galaxies began to form and ionize the intergalactic medium. The discovery of SDSS J0100 plus 2802 has also raised important questions about the formation of such massive quasars. It challenges current models of black hole growth and suggests that there may be other processes at work that we do not yet fully understand. For example, It has led to renewed interest in the idea of direct collapse black holes, which could form very large black holes directly from collapsing gas clouds without first forming stars. Quasar 3C273 is one of the most famous and well-studied quasars in the sky. Discovered in 1963 by the British astronomer Martin Schmidt, 3C273 was the first quasar to be identified as a quasi-stellar object, leading to the recognition of quasars as a distinct class of astronomical objects. Located about 2.4 billion light-years away in the constellation Virgo, 3C273 is the brightest quasar visible from Earth and can even be seen with a small telescope. 3C273 is significant for several reasons. First, its discovery marked the beginning of a new era in astronomy, as it was the first time astronomers realized that objects so far away could be so bright. Before its identification as a quasar, 3C273 was thought to be a star within our galaxy. However, the analysis of its spectrum revealed a high redshift, indicating that it was much farther away than any star, and therefore much more luminous. This discovery opened the door to the study of quasars and other active galactic nuclei, leading to a deeper understanding of the universe. Another important aspect of 3C273 is its role in testing and confirming various theories in astrophysics. For example, 3C273 has been observed across the entire electromagnetic spectrum, from radio waves to X-rays, providing a wealth of data that has helped scientists understand the mechanisms behind quasar emissions. It has also been instrumental in studying the structure and dynamics of jets, as 3C273 is known for its powerful jet of particles that extends several thousand light-years from the quasar. Observations of this jet have provided insights into the behavior of relativistic particles and the interaction between quasars and their environments. 3C273 is also significant in the study of supermassive black holes. The quasar is powered by a black hole with a mass of about 900 million times that of the Sun. The accretion disk around this black hole emits vast amounts of energy, making 3C273 one of the most luminous objects in the universe. By studying 3C273, astronomers have been able to learn more about the accretion process, the structure of quasar jets, and the role of supermassive black holes in galaxy evolution. One of the enduring contributions of 3C273 is its use as a standard candle in astronomy. Because it is so bright and well understood, 3C273 is often used as a reference point for calibrating instruments and measuring the brightness of other celestial objects. Its well-studied nature makes it a valuable tool for both observational and theoretical astrophysics. The study of quasars like SDSS J0100 plus 2802 and 3C273 is crucial for our understanding of the universe. These objects provide a window into the past, allowing astronomers to study the early universe, the formation of galaxies, and the growth of supermassive black holes. Quasars play a crucial role in helping astronomers measure distances across the universe. Because they are incredibly bright and can be observed at great distances, quasars act as cosmic lighthouses, allowing scientists to gauge the scale of the cosmos. The further away a quasar is, the longer its light has taken to reach us, which means that by observing quasars, we are looking back in time and seeing the universe as it was billions of years ago. This unique ability makes quasars invaluable tools for measuring vast distances and understanding the structure of the universe. One of the primary ways quasars are used to measure distances is through a technique called redshift. As the universe expands, light from distant objects like quasars is stretched, causing it to shift toward the red end of the spectrum. The greater the redshift, the farther away the quasar is, and the older the universe was when the light was emitted. By measuring the redshift of a quasar, astronomers can estimate its distance from Earth. This method has allowed scientists to map the distribution of quasars throughout the universe, helping to chart the large-scale structure of the cosmos. The cosmic distance ladder is a series of methods that astronomers use to determine distances to celestial objects. It starts with measuring the distances to nearby stars using parallax, then moves to more distant objects like galaxies using standard candles such as Cepheid variable stars and type Ia supernovae. Quasars, due to their immense brightness and high redshift, extend the cosmic distance ladder even further, reaching into the farthest regions of the universe. While quasars themselves are not typically used as standard candles because their brightness can vary, they play a crucial role in calibrating other distance measurements. For example, quasars can be used to refine the Hubble constant, which is the rate at which the universe is expanding. By comparing the redshift of quasars with the distances calculated using other methods, astronomers can improve the accuracy of the cosmic distance ladder. This in turn leads to a better understanding of the scale of the universe and its rate of expansion. Quasars also help in understanding the distribution of galaxies and the large-scale structure of the universe. By studying the light from quasars as it passes through intergalactic space, astronomers can learn about the distribution of matter, including dark matter, in the universe. This information is critical for refining models of cosmic evolution and for understanding how the universe has grown and changed over billions of years. One of the most significant contributions of quasars to cosmology is their role in refining our understanding of the expansion of the universe. By observing quasars at different distances and redshifts, scientists can track how the universe has expanded over time. This helps in testing theories about the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Moreover, quasars are used in gravitational lensing studies, where the light from a distant quasar is bent by the gravity of a massive object, like a galaxy, that lies between the quasar and Earth. Quasars are essential tools in modern cosmology. They extend the reach of the cosmic distance ladder to the farthest parts of the universe, help refine our measurements of cosmic distances, and play a critical role in our understanding of the universe's expansion. By studying quasars, astronomers continue to unlock the secrets of the cosmos and refine our understanding of the vast distances that separate us from the most distant objects in the universe. Studying quasars requires a variety of observational techniques, each of which helps astronomers gather different types of information about these distant and powerful objects. Quasars emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays, so astronomers use a range of instruments to capture and analyze this radiation. These techniques allow scientists to understand the physical properties of quasars, their distances from Earth, and the environments in which they exist. Spectroscopy is one of the most important techniques for studying quasars. It involves spreading the light from a quasar into its component colors, much like a prism spreads sunlight into a rainbow. By analyzing the spectrum of a quasar, astronomers can learn about the composition, temperature, and motion of the material around the supermassive black hole. Spectroscopy also allows scientists to measure the redshift of a quasar, which provides information about its distance and the expansion of the universe. Quasars are powerful sources of radio waves, and radio observations are essential for studying these objects, especially when their light is blocked by dust or gas. Radio telescopes, such as those that form the Very Large Array in New Mexico, detect the radio waves emitted by quasars and provide images of their structure, including the jets that extend from the black hole. Radio observations are particularly useful for studying quasars that emit strong radio waves, known as radio-loud quasars. These observations can reveal the size and shape of the jets, the rate at which they move, and how they interact with the surrounding intergalactic medium. Radio data also help in mapping the magnetic fields around quasars and understanding how these fields influence the behavior of the jets and the accretion disk. Space telescopes play a critical role in studying quasars, especially in wavelengths of light that are blocked by Earth's atmosphere, such as ultraviolet and X-rays. Telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory allow astronomers to observe quasars in these wavelengths, providing a clearer and more detailed view of their structure and behavior. Hubble's sharp imaging capabilities have been used to study the host galaxies of quasars, revealing how these galaxies interact with the quasar at their center. The Chandra X-ray Observatory detects the high-energy radiation emitted by the hottest regions of the accretion disk and the jets, giving insights into the extreme conditions near the black hole. Space telescopes are also vital for observing quasars at great distances, where their light has been red-shifted out of the visible range, requiring observations in the infrared or other wavelengths. The study of quasars relies on a combination of techniques, including spectroscopy, radio observations, and space telescopes. Each technique provides a different piece of the puzzle, helping astronomers to build a complete picture of these fascinating and powerful objects. By using these tools, scientists can continue to explore the mysteries of quasars and deepen our understanding of the universe. As our understanding of quasars continues to grow, so do the challenges that future astronomers will face in studying these incredible objects. One of the most significant challenges will be the need for more powerful telescopes. Quasars are often located at the farthest reaches of the universe, which means their light has traveled billions of years to reach us. As a result, their signals are extremely faint by the time they arrive at Earth. To study these distant quasars in greater detail, astronomers will need telescopes with even greater sensitivity and resolution. These telescopes will need to capture light across various wavelengths, from radio waves to X-rays, to provide a complete picture of the quasar's properties. Interpreting data from distant, high redshift quasars will also present challenges. High redshift quasars are those that are located so far away that their light has been significantly stretched or redshifted as the universe expands. This redshift makes it difficult to analyze their light using current methods, as the signals are often weak and spread out over a wide range of wavelengths. Future astronomers will need to develop new techniques and technologies to accurately interpret this data. As we look further back in time, we encounter the universe in its younger stages, when galaxies were still forming and the first supermassive black holes were just beginning to grow. The conditions in these early environments are very different from those in the present-day universe, making it harder to apply what we know about nearby quasars to those in the distant past. Future astronomers will need to develop models that account for these differences, including how the intergalactic medium interacts with the quasar's jets and radiation. Additionally, there will be challenges related to the sheer volume of data that will be collected by future telescopes. With the advent of new observatories like the James Webb Space Telescope and the Extremely Large Telescope, astronomers will have access to an unprecedented amount of information. Managing, analyzing, and interpreting this data will require new approaches, including advances in artificial intelligence and machine learning. These tools will be essential for identifying patterns and trends in the data, as well as for making new discoveries. Finally, one of the biggest challenges will be pushing the boundaries of our current understanding of physics. Quasars are some of the most extreme objects in the universe, and studying them can reveal new insights into the laws of nature. However, as we explore these extremes, we may encounter phenomena that cannot be explained by our current theories. This will require astronomers to think creatively and develop new theories that can account for these observations. The study of quasars could lead to breakthroughs in our understanding of black holes, dark matter, dark energy, and the fundamental forces that govern the universe. Quasars are truly mind-bending phenomena that push the boundaries of our understanding of the universe. From their formation around supermassive black holes to their role as cosmic beacons that help us measure the vast distances of the universe, quasars continue to challenge and inspire astronomers. The study of quasars not only deepens our understanding of the cosmos, but also drives advancements in technology and theory, ensuring that the exploration of these fascinating objects will remain at the forefront of astrophysical research for years to come. As we continue to build more powerful telescopes and develop new techniques, the mysteries of quasars will undoubtedly yield even more extraordinary discoveries, shaping our view of the universe and our place within it. If you're ready to take your stargazing experience to the next level, check out the telescope and binocular links in the video description below. As an Amazon associate, I earn from qualifying purchases, but it won't cost you a penny extra. Thank you for joining us on this journey through quasars. Please like, comment, and share the video, and please do not forget to subscribe for more videos.